We all have questions. Big questions.
Can I journey into the past?
It's part of what it means to be human.
Is time travel just science fiction?
My name is Stephen Hawking, and I believe that anyone can answer big questions for themselves. So with the help of some ordinary people,
Wow! This is awesome!
and a team of experts,
You can't get a place in the universe where gravity is stronger.
we are going on the ultimate voyage.
Pulling them out of these!
A quest to answer the greatest mysteries of the universe, using the power of the human mind. Because anyone can think like a genius.
Can we time travel? Can we time travel?
Time travel is one of my favorite ideas. Most of us have dreamt of visiting a different age. Perhaps a peek into our own future. Or to see a monumental event in history. For decades, time travel has proved irresistible to science fiction writers and Hollywood directors. But can we work out if it is really possible to travel through time? I've asked 3 ordinary people to come on a journey of discovery. A series of puzzles and challenges await them. They'll be given equipment and instructions to help.
Wow! Nice.
Can they solve the mysteries and find the truth about time travel?
Can I travel in time?
I don't know. I don't know where to start.
I feel excited to contemplate the issue of time travel.
I'm gonna say no, but technology now, possibly in the future.
I don't know how or what the actual mechanics of it are, but I think it's possible.
Yes, I believe it is possible.
I brought my volunteers to New York City. What better place to begin their quest than Times Square? I want to see if my team can grasp how science began to explore this elusive thing we call time. I've lined up a surprise.
Oh, look.
Hello, my budding geniuses. Welcome to New York. I hope you are ready for some fun.
I did not expect Stephen Hawking. It was awesome. It was a complete surprise and complete shock.
I was flabbergasted to see his face there.
I'd like you to come to a party. Using these 3 numbers, can you work out how to get there? Good luck.
48, 16, 11.
Can we make it to a party using those 3 digits? 48.
48,
48, 16, 11.
Time to get thinking.
What do those numbers have?
In common?
Yeah.
What comes in 3 numbers? 48,
Triangle.
16, 11.
Length, distance, and width.
I can't think of a
I
mathematical
can't picture it
relation.
now. Could be like longitude and latitude. In
Or is
time,
it street?
Good thinking.
Yeah.
Is there a 48th Street?
there is a 48th Street. 16th Avenue would put you into the Hudson. So,
They stop there, do they? The numbers stop there.
yeah, because there's a river. Oh, so 48th Street, 11th Avenue, and maybe once we get to 48th and 11th, the 16 will present itself.
Yes. We can ponder it on the way.
Let's go.
I've asked the volunteers to make a video diary of their journey. They will need this later.
Okay, Marisol, what are we up to?
We're gonna go to a party.
Norma. Party, bro. We're on a mission.
We might be wrong, but we took that address be the one thing we could take action on.
All right, what street are we on?
This is, what is that?
46.
This is 7.
7th.
Made sense to follow the grid, like to follow the streets.
We are 48, the first number.
The first digit.
Selfie, guys, yeah.
Selfie.
Where are we?
48.
48 with us, and there's a sign.
Now off to 11.
So, yeah, 11th is that way. Hopefully, 48th and 11th was going to pan out. Or were we going to have to start all over? Here we go. 48th Street and 10th Avenue.
One more avenue to go. We were really hoping that we would come across some kind of divine inspiration.
Here we go. 11th and 48th, 48th and 11th.
They're right about the intersection of 48th and 11th. But can they use the third number to get them to the party?
I don't see anything in particular. We got the 48, we got the 11. That just leaves 16.
First, just saw the building. Nothing was screaming 16, but it was just like a really tall building.
1, 2, 3, 4, 5, 6. 16th floor?
16 floors. It had to be a level.
So let's check it out. Yeah?
Yeah, let's check.
All right.
Traveling through anything, be it space or New York City, means going from one place to another. Thanks to a genius who loved to lie in bed, science has a way to describe what this means.
In Europe in the first half of the 17th century, what became the scientific revolution began to gather pace as a new generation came along. Among their number was a Frenchman, René Descartes. He was esteemed in particular for his work in the study of nature, above all the mathematical study of nature. The story goes like this, that Descartes was a sickly child, and so he was allowed by an enlightened teacher to spend his mornings in bed. And indeed, Descartes found this so useful that he kept it up for the rest of his life. He found often his best thoughts came while he was in bed.
Descartes found inspiration in ordinary things. On one occasion, it was thought to be a common housefly.
One day, Descartes was in bed and he was idly watching a fly up on the ceiling. And as the fly wanders around, it occurs to Descartes that with just two numbers, one to describe its position along a horizontal axis, another to describe its position along a vertical axis, he can capture mathematically the position of the fly at any given moment. So there's Descartes watching the fly up on the ceiling, and at a certain moment it drops down. Now on the ceiling, the fly needed just two numbers for its position to be uniquely described. When it drops down, it leaves 2 dimensions and enters into 3 dimensions. Now we need 3 numbers. And it turns out that anything can be positioned using just 3 numbers.
In this simple stroke of genius, Descartes laid the foundation for modern mathematical science.
And this insight becomes the germ, or what we now call the Cartesian coordinate system.
The The Cartesian coordinate system is still in use today, especially in New York City.
All right, 16th floor.
16th
Yep,
floor.
go for it.
That's the last of our coordinates.
It allows us to precisely pinpoint a location, which is what you need for a party.
Stephen Hawking is up there waiting for us.
Probably.
That'd be good.
That'd be a surprise. That'd be a party.
Would have been a party. Hi guys, we're here.
We walk out onto the 16th floor, and there's a party.
Oh, wow!
It looks like we got the right spot. That had finished up some time ago.
There was a party.
There was a party,
It's
yeah.
over. We missed it.
It looks like they had a good time.
My initial feeling was one of massive disappointment to have missed what looked like it'd been a great tear-up. So,
Shucks.
Well, at least we're on the right path.
My invitation wasn't complete, so my volunteers have missed the party. Can they figure out why?
I'm sorry I had to go. How many pieces of information do you need to make it to a party?
how many pieces of information do you need to make it to a party?
48, 16, and 11.
So a point, so like an intersection, so
We got
two numbers
48.
for the point.
That's in 2 dimensions. Then your third dimension is in height. So we went that way, that way, that way. So that's 3 points of information. And the fourth piece of information would be time. So you'd need 4 pieces of information.
And we only had 3.
The additional one being the fourth dimension, time.
Yes.
So time is a dimension that we're traveling through, but we don't really realize it because it's always present.
And that's why we missed it. That's why we missed it. We get all the information we needed.
This was a mean trick to play, but they're right. You need 3 numbers to describe a place, but you need a 4th to describe an event. And that 4th is time.
It was more of a revelation than a disappointment.
Awesome.
We're used to what we can see, and you give me a height, distance, place. I can work with those because I can see it. Time is there working, but you're not aware of it. Things are always happening in that 4th dimension as well. I guess this goes beyond being fashionably late.
Cheers, guys.
Cheers.
Cheers, congratulations.
To travel in time, we need to find a means of traveling through the 4th dimension. But what does this really mean? To help understand, I'm giving my volunteers a tough new challenge. In the next phase of their quest, to discover if time travel is possible, I hope the volunteers will grasp a concept that revolutionized our understanding of the universe.
Mysterious?
If they can understand it, then they really will be thinking like a genius.
Thank you.
Thank you.
My pleasure. We're walking in, and at first, really, I wasn't sure what I'm looking at.
It's where we were.
Times Square.
And then we all see the maps of New York.
They're all the same map, aren't they? Look, Broadway, Broadway, Broadway.
Different
with different
times.
times. The maps were identical, save for the time.
This one says 50 minutes, 10 minutes, plus 20, plus 30, plus 40 minutes.
Each map covers the area of New York they traveled through to get to the party, and each represents a moment in time. The map on the light box is their start time in Times Square.
Norman, look, it's you with hair. No, mine's far too pretty.
I have asked them to visualize their journey from Times Square to the party in both space and time. Let's see if they can get the purpose of this.
Oh, I know. Each of these maps is a point in time, isn't it?
Right.
And we could put our positions on the maps where we were at that point in time.
7 maps, 7 figures for each of us, so it was pretty clear that each of us will represent a certain spot during the journey at a certain time.
Where do we start, guys?
Right here. Times Square, 43rd. We're
middle?
going this way. In the middle. You're on the...
Should we see who were 10 minutes later?
The camera was not just for selfies.
We're gonna go to a party.
Hopefully, it will come in handy.
We were able to plot where we were because we had the time signature on the video. Do you see the street sign?
46.
So at 10 minutes, we got to 46th Street. Let's do it.
You take your time, Norm.
It just kind of seemed natural to stack the glass grids of Manhattan into layers and to place us in each time label that was on each table. All right, then the next one, I think it's plus 20. So if you guys want to grab it.
Yep, sure. To me, to you, to me, to you. Where are we? 48 with us.
This is the end of our first block.
48th Street.
That's when we turn left.
And then we go to 30 plus 30.
30. Good job, guys.
Precision engineering, Norman.
Have to update our resumes.
So 40 minutes. There we go.
45.
All right, so we are on
Destination.
11
And here's 48.
48th
Yep,
at the party. There we go.
that's us.
We did it, guys. Awesome.
We've built a path where we started and when we finished in space and time. So you can think of each layer as the spatial dimension, couldn't you? And each level, if you like, as the time dimension.
Which is the fourth
The
dimension.
fourth dimension.
Yeah. So we kind of plotted the fourth dimension. So where does that get us?
The conclusion I hope they will reach is one that was dreamt up by a clerk in Switzerland. He would become the most influential physicist in the 20th century.
If you were placing bets on who was about to revolutionize physics, you wouldn't have bet on Albert Einstein. 26 years old, a violin-playing bohemian, working not in one of the great labs, but in the Swiss Patent Office in Bern, where he was a lowly patent examiner. But Einstein toiled away on some of the most fundamental problems of the day. Because in Europe at that time, one of the most pressing practical problems was about how to coordinate the clocks so that the trains ran on time. And Einstein was examining systems which purported to do that.
Perhaps this work inspired him to start thinking about time. In 1905, Einstein published a paper which changed the way we see space and time.
Before Einstein, the conventional view was that space and time were two completely different things. Space was a kind of grand container holding objects and events, whereas time was a universal flow carrying everything from the present into the future. Einstein came to a completely different view on space and time. They were not independent of one another. They were aspects of a single thing, a single fabric of space-time. Everything unfolding within those 4 dimensions always.
Before the volunteers can really understand how we might travel through time, they'll need to make the same intellectual leap that Einstein made.
We realised it was a model of our journey. I think the realisation of what it meant came quite a bit later on, though.
Traveling through time with this visual, it seems like moving up, moving forward.
I mean, ultimately, I think we want to be able to manipulate where we are and when we are. and that the two are intertwined. Now with this, you can see you can't separate space from time, even though we don't typically look at it that way.
Are you saying it's not space and time, it's space-time?
Space-time. You might as well just lump it all together. It's no longer separation, for now we have a space-time map. So both are all in the same.
Norman, we've brought together the 4 dimensions.
They've got it. They have seen that their journey through space and their passage through time are inextricably linked. Time and space do not exist separately. They are unified. Space-time fills every corner of the universe, and always has. Every event in our lives has a unique reference point within it, both a physical location and a specific moment in time. The same is true for every particle in the cosmos, and every moment in history.
I won't look at it the same way anymore, because I am where I am, and I'm also when I am.
Space-time, it's the same thing, and you can't separate them. So we'd have to manipulate both to travel through time.
Most people think of time travel as a sudden disappearance from one moment in time and an instantaneous arrival in another, usually involving a cleverly engineered time machine. I hate to be a killjoy, but I doubt it will ever be possible to jump through space-time in this way. To understand time travel, we need to think of it as a journey. An expedition either forwards or backwards along the fourth dimension. Having grasped the concept of space-time, the volunteers are ready to come to grips with time travel. For their next time travel challenge, my team need plenty of room, so we've left New York and come to the beautiful desert of Arizona. I want them to imagine traveling backwards in time.
Yeah, look, lanes.
And there's another surprise in store.
So I'm walking in, and there's a dirt area, and there's 3 tracks.
Look at this.
Eros.
We got 2 forwards.
What's that one say down there?
Yeah, let's check it out.
There's a lane with the arrow pointing away from us that says forward.
The second lane says back and was labelled back.
And then the next one is the 3rd track with forward again.
2 forward, 1 back.
Imagine this is a magical parking lot that will allow them to travel through the dimension of time. But to do that, they'll need a time machine.
To our absolute amazement, the DeLorean came spinning round the corner. And then the driver jumped out, wangled keys in front of us. And no right-minded person confronted with DeLorean keys would not grab them.
Awesome. Instructions. Imagine this is a magical parking lot.
Imagine each lane represents the same passage through space-time. In the first lane, they will be traveling forwards with time, in the usual way, just like the rest of us. In the second, they become time travelers, as they retrace their route backwards through space-time, to the moment they began. In the third lane, they will be traveling forwards with time, in the usual way once again.
You must complete all 3 lanes of the course But before you set off down each lane, think about what you will see.
Their challenge is to predict
All 3 lanes.
what it would look like to travel backwards in time.
The first time we go down, we'll see nothing out of the ordinary, except us in the DeLorean. We get to the end, we come back in time, and at some stage we will pass ourselves going forward in time, won't we?
Yeah.
Are you sure?
Norman is right to question this plan. It has a flaw,
Here's the radio. We'll call you from the future.
All right.
but perhaps once they're underway, they'll spot their mistake.
Time to fire up the DeLorean.
Fired up.
We're in the DeLorean. Into the future. Our initial thought was, when we came back, we thought that we would pass ourselves, or we would pass ourselves about the halfway point. We hadn't considered at that point what we had missed. Let's line it up ready to go back to the past.
All right.
Okay. Right, let's give Norman a call.
Hey, Norm, what we should expect to see when we go backwards through the space-time is ourselves. There's going to be another DeLorean just passing by. What do you think?
I don't know.
They're right about one thing. If they journey back through space-time, they would see themselves. So for that, they're going to need another car.
All of a sudden, another DeLorean appears where we were, and to our utter amazement, well, then it's not one DeLorean, now there's 2 DeLoreans.
Norm, who is that? Is that us?
Yeah, yep, that is you.
Let's go back in time. Let's go back in time.
Let's see if coming face to face with themselves helps them realize their mistake.
Was actually us. Like, our faces were there, just staring at us.
We started to see flaws in our logic at that point.
I think this crossing of paths is what most people would predict. But I don't see backward time travel this way. They must think again.
So what would you expect to see if you retraced your steps back
Ooh.
through space-time? Well, think
We
about
would
it.
see, no,
You'd
it's see yourself go.
going what? You'll see yourself going backwards, wouldn't you? Imagine at the top of that space-time model and coming down it. You'll see yourself going backwards, wouldn't you?
Yeah.
Paul has spotted their error. If you imagine going forwards through the time dimension one way, then returning back the other, you would not cross paths with yourself. Instead, you would see yourself going backwards. Once you returned, you would continue to travel forwards with time once again. Only now, there would be 3 of you. Which calls for another car.
When we left, we created a new future, and that's when the 3rd car pops up.
To make this clear, let's try it once more from the beginning.
All right,
We're going to drive into the future.
from forward to back to forward. And here we go again. Oh, this is trippy.
In a linear journey through space-time, Paul and Marisol would see their future selves traveling back in time and moving forwards with time after their backward journey.
3 DeLoreans. 1, 2, 3. when you move forward in time, lanes 1 and 3 are going in the same direction. Relative to lane 2, it's going backwards.
As they journey back through time, they would be flanked by their forward-traveling past selves and their forward-traveling future selves.
Everything is happening in sync. It all has to happen together. You're moving forward and backwards together.
Once they stop time traveling and time passed normally for them once more, they'd see both sets of their past selves still traveling through time.
It's so weird looking at myself. You look so serious.
Oh, and to them, it's going to look like we're going backwards in time.
There's a fundamental issue with backward time travel. Let's see if my volunteers have spotted it.
Coming back starts to get a bit problematic because we witnessed ourselves going forward in time, didn't we? So at that point, there's now 2 of us.
Something has to pop into existence and pop out, and
At the moment, my view is that it's not possible because I don't see how we can have 2 of us in existence at the same time.
That's what I'm saying. It always seems like it's...
yeah, I mean, making things out of thin air, that there's living, breathing creatures and mass and energy showing up essentially out of nothing. That's not going to happen. If you go back, you've created something that was never there in the first place.
You can't go back. We came to conclusion that most likely traveling back in time was impossible. So it was nice to actually have it checked off the list.
They're right. The laws of nature do not support the sudden appearance of such large quantities of new matter. In other words, duplicates of time machines and people could not flash into existence. So backward time travel is unlikely to work. It's disappointing, but I prefer to look on the bright side. At least history is safe from meddling time-traveling tourists. Now they've ruled out traveling backwards in time, my volunteers need to think about traveling to the future. We've come to the University of Arizona. The volunteers will be surrounded by inquisitive minds as they endeavor to find out if it's possible to travel forwards through time.
I see a line of clocks with no numbers and a chest. It almost looks like a treasure chest, a box.
Dare we?
Do we?
Oh,
1, 2.
What the heck?
There were several counters. They were counting devices.
It's a parachute.
Let's get it out.
In the beginning, we just figured it was packing to hold the counters, and then some inspiration came to us.
There's a plug over here. You want to give it a whirl then?
Definitely.
Here we go. Ready?
Yep.
Coming on. All right.
It inflates.
Shall I get underneath it?
Yes.
You got it?
Yeah, because it's got to come up.
Once inflated, they will have everything they need to work out how to travel to the future. Switching the clocks on may help.
Ah.
They're moving at different speeds.
They're all going different speeds.
Yeah, they are.
At first, it looked like they were running in some kind of random order. It became apparent when you stood back that they're actually running slower and slower and slower the further away you got from the first one.
What do you guys think?
There seems to be a pattern, doesn't there, in this one's whizzing round.
Yeah.
This one's going a little bit slower than that one.
Right.
Time is behaving strangely near their inflatable. But will this help them work out what it represents?
We wasn't too sure what the significance of it was.
Looked like a planet at first, and then realized it was a black hole. Black hole?
Black hole.
Black holes are stranger than anything dreamt up by science fiction writers. But they are firmly science fact. A black hole is a star with an extreme amount of mass compacted into a relatively small amount of space. This mass creates the strongest gravitational field in the universe. A field so strong that the star's own light cannot escape, which is why they are called black holes. Albert Einstein discovered how they function when he turned his attention to something that had been puzzling him: gravity.
So Einstein said, none of you guys, none of you physicists really has an adequate theory of gravity, and I don't either, but I'm going to come up with one. What Einstein came up with is that the presence of mass actually bends or warps the shape of both space and time in its surroundings. And other objects then follow their natural paths through this intrinsically curved space. That's what the sun does, so Earth orbits it. That's what Earth does, so the moon orbits it. That's what the moon does, so rockets that we send up there orbit it.
Einstein said this warping of spacetime is what creates gravity, and that it also alters time itself. And that time passes at different speeds, depending on how strong the gravity is. The stronger the gravity, the more pronounced the effect. He called his theory general relativity.
Well, most people reacted in a very puzzled and incredulous way when Einstein first said that this is what gravity is. What the heck? What are you talking about?
But when we apply general relativity to black holes, things get truly strange.
A black hole is a place where gravity is at its strongest. You can't get a place in the universe where gravity is stronger than what's in a black hole. In Einstein's general relativity, the passage of time slows down to a halt at the boundary of a black hole. Regions near the mass are bent or curved more, and in a similar way, time is slowed down more.
This is a hard concept to grasp. Let's try an experiment to make it clear. Can the volunteers work out how warp time near a black hole can be used to travel to the future?
Can you use a black hole to travel to the future?
Yeah.
So if you were standing at the furthest clock, time would appear to be going very slowly to you, wouldn't it? Compared to somebody here.
Mm-hmm. Yes.
If you came back from that point to here...
Time had already been going ahead, so you're in the future.
Exactly.
Okay.
We staged ourselves, one at the nearest clock and one at the furthest and one in the middle, and we did counts of how many times we went past midnight. We'll sync on 12. And go.
1, 2, 3, 4, 5, 6.
They are getting the idea. The speed at which time is passing is relative to their proximity to the black hole.
3.
I was counting on the fastest clock, and when I got to 20, we all stopped. 19, 20, stop!
Stop! We're coming back
All right,
to
guys.
the present. Yeah.
All right, guys, what did you get?
This is how many units of time have passed. Let's call it days.
We'll call it
Days.
days.
We'll
Okay,
go
after
on days.
3.
All right.
1, 2, 3.
3.
How many you got?
1.
20.
Well, I'm on 5. So let me get in the middle.
All right. So I saw 1 day, you saw 5, and you saw 20.
I saw 20.
So we can use a black hole to travel to the future.
Awesome.
It seems counterintuitive, but hanging out in a place where time passes slowly allows us to travel to the future. When we return to where our journey began, we will have experienced less time relative to those we left behind. But to do this in reality, we would require a spacecraft.
I'll give you a countdown.
Countdown.
5, 4, 3, 2, 1. Engines go!
We were outfitted with the latest and greatest equipment for making the trip to the black hole.
Timing, Captain.
Pulling a lot of G's. Pulling a lot of G's. You could look at it as just driving around in circles in a golf cart, or, you know, you're really focused. You're in a spaceship going around the black hole.
We're at 2.
Imagine Norman and Marisol have traveled 26,000 light years to the supermassive black hole at the center of our galaxy. If they managed to go into orbit without getting sucked in, time would pass normally for them. But they might come back millions, even billions of years later.
Welcome back to Earth, guys! You've been gone 70 years!
Wow.
We got 3.
Oh, so you guys have come into the future. Welcome to the future.
Thank you.
Thank you. Only 3 years have gone by.
Wow.
There you go. We can use a black hole to travel forward in time.
Though it is not the jump through time that popular culture prefers. This is a method of time travel that is theoretically achievable. But can my volunteers work out why time behaves this way around a black hole?
As I think about it, as the gravitational strength gets stronger and stronger, I would expect time to actually speed up, not slow down. Oh, of course. You've got time and it's being stretched. So, of course, if I take one unit and stretch it, it's worth more of the other units the further you go. And, of course, the closer and closer you get to the black hole, the more and more time gets stretched. That's the explanation, isn't it?
Paul's got it.
It's amazing. To see it play out like this.
Yeah, to actually be in it physically.
Yeah.
Awesome, good job, guys. So it's not so much as learning how to manipulate space-time. It is just finding the location where space-time is already distorted and altered, and then using it to our advantage in order to go into the future.
If you could imagine a theoretical space journey for a length of time, come back younger than your children. So yeah, it is a crazy idea to think that, you know, you will literally be travelling in time.
Now they've worked out that we can use the warping of spacetime to travel into the future. They are ready to attempt this for real. Here, on Earth. As my volunteers try to discover whether we can travel through time, I've arranged for them to attempt a highly unusual experiment. Over the next 24 hours, their challenge is to send one of them into the future, right here in Arizona.
And yesterday's challenge was using a black hole to travel to the future.
The use of the black hole for traveling through time was because of the intense gravity there.
Sure.
So we do have gravity here.
This is the perfect place to try time travel. Let's see if they can work out why.
I would guess we can use our physical locations to give us 2 reference points. We just need to go higher, and I can see something right in front of us that let us do that.
Like what, Paul?
Like that mountain over there. You could have one at the top of the mountain, one at the bottom of the mountain. That gives us the same thing we had yesterday. We need clickers, basically. Yeah, we need some really good clickers. Yeah, that's what we need.
They are on the right track. Just like with a black hole, gravity is stronger near Earth's mass, making time pass more slowly. High on a mountain, further away from Earth's mass, gravity is weaker, and time there passes faster. To see the time difference, I've arranged for a world expert on clocks to loan them some impressive equipment.
So Tom opens the back of his trunk
Wow.
and it looks like old, like 1980s computer servers, all with a clock, 6 of them going at the same time, like exactly at the same time.
These are cesium atomic clocks.
Atomic clocks.
They are. They are so accurate that it takes millions of years for there to be 1 second of error.
Perfect.
So we've got a challenge that's going to require us to have a clock with a higher elevation. So if you could lend us a couple of clocks.
Sure, you need at least 2 clocks, no problem.
Yeah.
The clocks have been set to Coordinated Universal Time. Right now, they are all perfectly synchronized to each other,
Perfect fit. Yeah, good to go.
though they are
Close the lid.
stunningly precise. Cesium clocks are fragile, and it's going to
there we
be
go.
cold where this one's going.
Okay, watch out for yourself. Look at these.
Okay.
All right. Well, we're going to go up. You stay down, and we'll see you at the end.
By climbing to a high elevation, Norman and Marisol should experience a different amount of time to Paul, who will remain closer to the mass of the Earth.
Gonna be fun.
Tomorrow Paul can join them on the mountain to compare their clocks and see how gravity has warped spacetime.
The landscape is beautiful and keeps on changing. We get higher and higher, and then suddenly the cactus around us disappeared and then turned into like alpines and snow.
It's a world of difference being up and out of the desert.
Completely different world.
The higher they climb, the weaker the Earth's gravitational pull becomes. It's not by much, but time is passing faster as they go.
I don't know how much higher we can get, but I think we are doing a good job about reaching the highest elevation we can.
Yeah, looks like we're almost at the top.
Oh, look at the dome.
Nice.
We saw the tower was the highest point,
All right, let's get the show on the road.
and it's like we've already come up, 6,000 feet or so. Do we really need to bring it up that last little bit to get it up the tower? But, if you're going to do it, then do it.
Oh my gosh. That is heavy.
This better work. I'm not doing that again.
All right, let's see.
So we got it up here.
And we are at
What do we got? 9,091 feet.
nice.
At the peak of Mount Lemmon, they've reached 9,091 feet. Below, Paul is at 2,357. The differing strengths of gravity over this range should be enough to allow them to time travel on Earth. Their task for the next 24 hours is simple. Sit back and wait, perhaps with some light reading, while the warping of space-time takes effect.
Oh, Norman, how are you?
Oh, I'm fine, Paul. I could not be better.
I'm glad to hear you've not been eaten by mountains or
But so far, it's still early.
Yeah.
Do you have an idea of what possibly is going to happen tomorrow?
Well, I'd expect my clock to run a little slower than yours. I'm closer to the centre of the Earth than you are. I don't really know what the difference is going to be. So yeah, I'm curious to see. I'd be interested to see what the difference is.
In their attempt to travel into the future here on Earth, my volunteers' 24-hour wait is over. By comparing their clocks, we can see if they've accomplished their goal.
Guys, how are ya? How was it?
Good.
This is going to be very tricky.
Do it. So 24 hours later, we transfer Paul's atomic clock up to the tower.
Then it was just kind of waiting to open your Christmas present to see what was in there.
Are you ready for your results?
Yes.
Here's the clock that we brought up yesterday.
Yep.
It's been up here, probably running faster, gaining time. Here's the clock we left down at the hotel for the whole day. We think this clock should be ahead of this clock. And the answer is 20.485 nanoseconds.
Nanoseconds.
20 billionths of a second.
Just seeing the number was amazing because it actually did happen.
Oh my gosh.
That's the difference between these two clocks.
And that was time travel. That was time travel.
It's kind of unbelievable and amazing that it could actually be calculated and it can actually be done within 24 hours.
Having joined him at the mountain top, Paul has traveled into their future by 20 nanoseconds.
It's incredible. I was 20 billionths of a second behind the other clock. So really, I am 20 billionths of a second younger than the other two guys.
Just like with the black hole, by being near the mass of the Earth, Paul has experienced a slower passing of time than Marisol and Norman.
Wow, look at the view!
They are truly time travelers.
Wow, look at that. Thank you.
It's pretty unbelievable that you were just down there and we just took a quick trip up the mountain and time sped up. Our clock was faster up here. So it's just cool that we can have like binoculars and just look at people down there and technically they're in the past.
The idea of time travel, where it's always seemed as this far-fetched thing, it's happening all the time, albeit in little tiny increments. The world is working in a way that you hadn't really paid attention to.
You,
sir, have traveled into the future.
So you've allowed me to join you. I have time travel. Join you in your present.
Time traveler.
Time traveler. Is that worth a high five?
Yeah.
It's an incredible demonstration of how gravity affects time. You can, by definition, move forward through time.
Hello, my budding geniuses.
In the beginning, I was thinking time travel. It's just like a ridiculous idea. So it's pretty amazing to actually get an answer.
20 billionths of a second.
Wow.
Yes, we can travel through time. We did it. We actually did it.
The volunteers have come a long way on their journey. They've understood that the fourth dimension of time is unified with space into the single entity of space-time. Traveling to the past has been ruled out, but they've learned how to use gravity's warping of space-time to travel to the future.
Each challenge has helped build a better understanding of how time works, not just what it takes for time travel, but how it actually works, and it's good to have.
You've been gone 70 years! Wow. So we've come to the conclusion at the end of the week that it is possible to travel forward through time. Wow! And yeah, it's a lovely feeling to draw that conclusion, to have those eureka moments. It's got to be worth one then. Come on!
We all travel in time, all the time. When you fly in an airplane, climb a mountain, or use an elevator, you are altering the speed at which you get to the future. As for me, it's time to go.